Okay, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera pada semua. Untuk yang mengambil kurs JIF 314 untuk thermodynamics. Ini kuliah pertama lah kita. Okay, saya akan mulakan. No. Okay. To have a few topics, okay, like you have in your e-learning. So we're going to have around 7 chapters. Sorry. So starting with this simple thermodynamic system, introduction part, and we're going to finish until the entropy. Okay. So good. Our session with the introduction to thermodynamics, and because to me it's very important, we get a very clear view of thermodynamics, and to reduce the nerve. Don't be scared with this thermodynamics. Okay, so basically we are for the topic we are not going to encounter with a lot of calculations. Just a few equations here. Okay. Basically, in this first topic, we're going to discuss about the simple thermodynamic system, and going to have thermal equilibrium temperature, property of system for thermodynamics, past, process, and cycle, temperature, pressure, so on, until the zeroth law of thermodynamics. Then only we are for the next topic we go towards deeply on heat, work specific heat, and also law of thermodynamics. Now, basic thermodynamics. Okay, so it's actually a science of the flow of heat. Okay, of heat flow. In other words, so the term stands for heat. The dynamics is motion of heat. So you have motion of heat in certain situation or system, what we call a system. So where it begins with the burn of fossil fuels, where there is the initial problem of carbon dioxide and the global warming. Okay, so we go to study the effect of different substances. Okay, so the energy storage, the condition process, the applying equilibrium states. And so we're going to use several processes similar to this in our daily life, such as heat of water to make coffee, to generate the turbine. Okay, we have the thermal power, and so how we can actually identify the refrigerator process. Okay, in the refrigerator system to make water or ice cube. Okay, so in here, so we're going to study all these things related to the thermodynamics. Now, okay, so basically, I think you already know about this law of thermodynamics. From what we know, we only have like how many? 2, 3, three. First law of thermodynamics, second law of thermodynamics, the law of thermodynamics. Okay. For me, it's actually we're going to have 4 laws of thermodynamics. I'm going to introduce one by one to you guys. Okay. The first law of thermodynamics. Okay. This law is one of every one of these laws basically defines the quantity of thermodynamics. Okay. The zero defines the temperature. Okay. That's a fairly common sense idea, but it's important to define it. Okay. I call it as a common sense law. Okay. So in the for sense law, it's all about temperature. Means the amount of energy, range of energy. Okay. So secondly, you're going to have the first of thermodynamics. Okay. The first of thermodynamics, it defines the energy. Actually, we are going to call it as U. There is the internal energy, and the concept of the energy conservation, which energy can't be lost or gained. Okay, and I'm to call this that you can break even law, because you don't lose energy or you can't get any energy. So you break even. So next is the second law, okay, which is related to the entropy. So basically, you might ask, oh, what is all about this entropy? It's actually a thermodynamic quantity representing which interpret the disorder of a dynamic system. Okay, because it depends on what kind of substance that you use for that system. Now, well, basically, to explain to us about the direction of time, something that we clearly understood as mathematically in thermodynamic physics. Okay, so finally, I hope you can see all this. Okay, if you come this, please let me know. Okay, now law. Okay, we're going to the third law, thermodynamics. Okay, I remove here. Okay, so it's a numerical to entropy. It's something like this. You're going to I'm going to say I'm having a crystal ball, and I'm going to throw it to the ground, and it's going to break into pieces. So that crystal ball going to break with condition that it's going to hit the floor. Okay, so that's why you get it to 0 Kelvin. Like the second law, sorry, I forgot to mention, I call it you can break even only at the 0 Kelvin. Because in the second law, or the entropy will agree the rules will have 0 Kelvin. Now, for the third law, I call it you can't get to 0 Kelvin, because it's so, what do you call that, ideal. So that's why all laws actually universally, although it's universally valid, it actually belongs to the classical physics, like classical physics, because no laws at all. So we know that in real life, we're going certain parameters, we're going to have some loss in terms of energy. Okay, to the links. Now, so basically, what is thermodynamic system? We need to actually identify what is the system, the relation with the thermodynamic. So in order to understand the thermodynamic, you need to have a system. So it's part of the universe. So you're going to have matter with space, and it's going to have a boundary. So example, we're going to have ice in a glass of water. Okay, so ice is the system. Okay, a glass of water, and it considers the whole system of thermodynamics. Okay, it's a state of matter. Okay, so the surrounding will be the atmosphere, bounded with the glass. Okay, so it's important, okay, to place the boundary at the right place. So much or less will affect the thermodynamic system. Basically, you're going to have a system, okay, with a real boundary or imaginary boundary. So normally imaginary boundary is just like air. Okay, it's going to be amount of energy going in and going out of the system. Okay, so important for your basic understanding what is the thermodynamic is all about. Okay. Now, okay. All right. So, dynamic system, we have one particular system. It can be an open system, it can be a closed system, and it can be an isolated system. Okay, so for the isolated system, it's going to circulate only in that particular system. Okay, like what you have in the refrigerator system. Okay, it's going to circulate all over again. Okay, so and the energy transfer through the boundary, but not the mass. This is a closed system where you have the thermos. Okay, and where you have the thermos, energy transfer through, not amount of mass, so it's going to reduce. But a very good thermos is going to have in the group of isolated system. Okay, so now you're going to have also the open system where the mass and energy free flow through the boundaries. Going to have different nozzle towards the turbine, so that is a system within a system. The refrigerator system, so you're going to have another system related to the heat sinking flow of the fluid. Basically, this is what the figures look like. Okay, for the system and also and the system. Okay, and for system, it is also known as a control system. Okay, a closed control system. Open system, you're going to have also as a control volume, and for the isolated, so for the boundaries, you're going to have a control surface. Okay, of the part. Now, basically, it look like this. Okay, a simple thermodynamic system where you have one particular system and you have surrounding and you have the boundaries. Okay, so the quantity of matter in one particular space for space, and the mass of the region outside the system is the surrounding. So then you're going to have a boundary. It can be real and it can be imaginary. We fix it, and there's particle thickness or volume towards the boundary. Okay. Basically, okay, this is what we call steam plant system. It actually involves a lot of thermodynamics concept towards it. So basically, you're going to have coal to a yellow, so you're going to grind, and additionally with the oil, you're going to have what I call it, the burning process. Okay, in the reservoir. Okay, to the water in the steam drum. So this amount of water going towards the sun. The whole thing. Okay, sorry. The whole thing. Okay, is a system, but it go to fit into a small system for the steam drum, turbine, and all the heat exchanger. So it involves a lot of thermodynamic process here and here. Adiabatic process. So that process will go in later. Okay. So now then we're going to have this. Okay. Now, so in that, sorry, go to this. Right. Okay. So towards the turbine and the steel drum, so it's going to heat up the water. So it's going to, when it relates with the temperature, it's going to increase the pressure in the reservoir, the steam drum. Okay, so you have it. Okay, a volume. So which is going to actually with high pressure towards the motor, is going to actually we have a control volume process towards the surrounding. So it's going to actually activate this means the turn the turbine. Okay, so So the surface may be open to close or close to the mass flow. Okay, so now equilibrium and also the temperature. Now we're going to have a behavior of the system investigating the microscopic or the macroscopic point of view. Okay, if let's go towards the microscopic, so we're going to consider a system with 25 millimeter cube, okay, cube side by side with a monoatomic gas at the atmosphere. Okay, so basically we're going to have that. Volume contain like 10 to the power 20 atoms. Okay, basically, can I have it? Yeah. Okay. So basically, going to have sorry. So we're going to have a system. Let's go later on. Okay. So this volume which relate with the amount of particles. Okay. So going to describe the position of each atom or the particle for different coordinate x, y, and z. Okay. To the velocity of each atom, we're going to specify the velocity component for the x, y, and z. So you're going to configuration in that particular system. So so the thermodynamics consider as a bird eye view. We focus on the reducing number of variables to a few that can be handled relatively easily involving the microscopic point of view. Okay. Property system. Okay. Typically, you're going to involve this property: the pressure, the volume, the temperature, mass. Intensively, you're going to independent on the mass system, actively dependent on the mass system, and we're going to have specific volume and also the enthalpy. So this is part of the system. Take to know for the means as time goes by. Okay. So since this is the first topic, I'm going to actually introduce on the pressure, volume, temperature, and mass system. Okay. So basically, you know about the you heard about the ideal gas law, right? So you have ideal gas law. Okay. Now let's go to here. So we're going to have ideal which involve PV equivalent to NRT, which P stands for pressure, volume, and this what is it, of moles, right? Okay. This is constant value of gas constant value. So we have around 0.082 atmosphere per Kelvin. Okay, and this is the temperature. So basically, how does it everything related to the we'll have it towards the pressure means the system. So I'm going to show afterwards, okay, how it relates. Okay, so the system be in open system, or it can be in the closed system or isolated system. Okay, the definition of all this system that we have here is important. Okay, so, an open system, as the name describe, allow mass and energy to freely flow through the boundaries. Mass flow and mass energy flow through the boundaries. So say we consider myself. Okay, I'm also part of the system. Okay, I'm hot. People say I'm hot. Okay, compared to the air of this room. Okay, we're going to have a system. So I'm part of the system in this particular room. So which you probably can see me or not. Okay, So the energy going towards back and forth. Okay, so basically to okay. Now we also have state and equilibrium of that system. Okay, so assume the system is not towards any changes. So we know at the state 1 we're going to have same amount of the okay, kilograms, with the second state 2 kilograms, but you see that there's a difference in terms of the volume. Okay, our properties to completely destruct is known as this state 1 as state 2. The properties that we have, the mass, the temperature, and when we actually include, okay, sorry, right, so you will have different volume. Okay, so to have less volume here, high pressure to have less volume. Sorry, less pressure going to have higher volume. Higher you're going to have less volume. Okay, basically is related with the amount of kinetic energy. Okay, because towards the equilibrium, okay, first at the first state, okay, you can see that the thermal equilibrium, there's no changes of temperature throughout the system. Okay, and phase equilibrium having more than one phase. The mechanical equilibrium, there's no change in the pressure, and the well, since it don't have any changes, so you're going to have phase equilibrium towards it, and also there will be no chemical composition, which normally is related to any kind of chemical, because when you have different temperature, different pressure, for certain chemicals, you're going to have certain reaction as gasoline. Okay, so you're going to be compact. So the path or the process, okay, because of all this, you I just explained to you, you need to understand when at the equilibrium state, you're going to have certain process. Okay, the property, it be pressure. Okay, it can be pressure. You're going to have temperature around here. Okay, so going to have a state 1 and to state 2. Okay, so with changes of temperature, you're going to have changes in the pressure. Okay. And understand, okay, going to have an equilibrium condition, okay, where stated a quasi-static, where we have T at 0, at T1, so for the non-quasi-static, okay, we consider a quasi-equilibrium process. So this quasi-static, quasi-equilibrium process, we're going to discuss more on this chapter, I think chapter 2. Okay, it's going to be under the chapter 2, the energy transfer. Okay, so this static will be like that means from the point we're going to have the T1 and T2 going to have a very significant difference. So we're going to have a non-quasi-static. Okay. So process for the quasi-static process, okay, so you're going to have a very significant path, okay, and you're going to have a continuous, okay. For the non-quasi-static, it will have bigger, but going to wait. Okay. So going to have the path to the non-quasi-static process path. Okay, so it's going to jump a lot bigger than this. Okay, it means That's it. In period slide is about the boundaries that we have. Okay, boundaries that we have. So different volume. So we're going to have stuff where you do have a constant volume. We call it isochoric. Okay, so it's a new term. Okay, and we're going to have isobaric. Okay, when we have a constant. Okay, so this is very important for us to understand later on with the phase diagram. Okay, in the thermodynamics. Okay, and also when we have enthalpy, entropy. So for the thermal constant process, we're going to have the isothermal. The enthalpy. Okay. So as this constant, you're going to have isentropic. Then also you have isenthalpic. So this part, have a look at the final chapter. Okay. Under the thermodynamic, we also have certain cycles. Okay, some words got means to these parts where we have the cycle. So it can be the what you call that one particular complete cycle. Okay, from state 1 like just now. Okay, so we're going to have and when you have a complete cycle, it's considered as the reversible process. Okay, so reversible process. So what can it be reversible? Yeah, at a certain point it can be reversible. Okay, so a system said to have undergone a cycle. So when it starts from state 1 to and to state 1. Okay, so it's reversible or irreversible process. So a process can be reversed without leaving any trace of the surroundings. So it's a very what you call that ideal situation. So this is only possible when the net heat and the change is equivalent to 0. So that relates with the second law of thermodynamics. Okay, so we will return to the initial state. Okay, so it's like a piston. When it turns, okay, T naught to become T1. Okay, okay. So when there's no any pressure, it's going to reverse back to the initial position. Okay, which means it depends on the kinetic energy. Okay. So there are which we can't have any reversible process. Okay, but you need to, let's say you have a cup of coffee. Okay, it cool when exposed to surrounding. Okay, but we need to gain heat, but we can't gain heat from surround, meaning without external heat. Okay, the coffee will not become hot anymore. Okay. The thing that you need to understand is why reversible process. It's going to for us to analyze as a physicist for a system in the refrigerator. Okay, system in the power plant system. Okay, so it's one particular ideal model. We have a Carnot cycle, the diesel cycle. So all these cycles will actually having the reversible process. Okay, but to consider this an ideal process. Okay, that's why I told you all, I told you guys that is actually what you call that, a class physics point of view. Okay. So just now, the zero identify about the temperature. Okay. So basically, what is temperature is just degree of heat present in the substance. Okay. There's no exact definition. As long as you have a metal, so the of heat substance or the heat going out of the substance. So that's considered a temperature. So you need when we have a thermometer, we have actually one particular scale to actually define this temperature. Okay. Now, for the temperature scale, as you know, we're going to have 4 kind of temperature scale. Okay. Let me have a look. So we're going to have the Celsius scale system, the Fahrenheit scale system, Kelvin scale system. So the SI scale system, the Rankine scale system. Okay. Only US and also Jamaica using this Fahrenheit scale and also Rankine scale system. So mostly under the standard, okay, going to use the Celsius and Kelvin scale system. Okay, so then you have dynamic temperature scale, which we focus on the Kelvin scale, so which in conjunction to the law of second law of the thermodynamics. So that's why we are more focused towards the Kelvin scale system. Okay. The common factors, this will be the conversion factors for the Celsius, Fahrenheit, and also Rankine. So in order to convert, so you have it in the degree Celsius, so you need to add 273, okay, exact 0.15 to the numbers, let's say 30 degrees Celsius, okay, degrees Celsius, so you're going to have it here around 303.15. So on towards the Rankine, also the Fahrenheit, and so also to the other way around of the conversion. Now, talk about the pressure. It's so important to identify this pressure, okay, towards the towards thermodynamic system based on the ideal gas law that we have. So the normal force exerted by a fluid per unit area. Okay. So with a gases, so normally we relate with the pressure. So for solid, normally with the stress. So pressure, okay, I know, sorry. Okay. Now, when you pressure, okay, normally, like I said, it related to the kinetic energy, right? Say these that have in the closed system. Okay, these will be the particles in the closed system. So basically, this particle will not be static, so it's going to be dynamic, like we said. So it's going to be dynamic, and then going to move here, like Brownian motion here and there, and then we have a lot. Okay, this is only 4. So basically, this so you're going to increase, means it's actually going to increase the pressure. Well, particles actually decrease the pressure. Why? Because basically you're going to have, let's say we are focusing more only, sorry, again, different pen, this part. So we're going to have here, and here is the particle. So as it moves, okay, as it moves, it's going to hit the wall. In different direction, x, y, z direction, because we are in 3-dimensional. So we need to have certain average energy, what we call the temperature. So when we increase the temperature, so it's actually the average energy for what we call we start with J is the temperature. So you have T equivalent to energy over particles. Because relate with the number of moles. Okay, we have it as a cube right now. So hit the wall, okay, then it will develop with the pressure. So it's going to develop pressure. That's why you have pressure equivalent to force over the air that we have around here. Okay, so B, that's what have P equal to F over A. Like I say, I'm going to introduce a little bit of equation related to here. So basically, the force when it relate with the pressure, so you're going to have the force also. Okay, you have changes in momentum. So this is what we call is momentum. Okay, over changes of temperature. Okay, so it really each other. Okay, that's why we have a force. Okay, we actually relate with the particles momentum, different temperature that occurs. Okay, when it occurs at certain particular area that we have it, this is the area. So you're going to have changes in pressure. So that's why you're going to have different pressure, and that's why it relates with the dV equivalent to nRT. Okay, so it relates with the kinetic energy. So that's why when you have relation with volume, so because what we discussed here is only like 2-dimensional, we go to different volume. Let's have all the particles here. Okay. L P equal to constant. Okay, then you're going to have a constant. You have average kinetic energy. Oh, really? I'm done right now. Okay, the most important part is for your understanding, basic understanding. So kinetic energy will go here and here. So let's say we take it as 3-dimensional. Okay, let's say the volume going sorry about that, it pop up. Okay, now volume is reduced. Okay, let's say the volume is reduced to a smaller, but with the same amount of kinetic energy. Okay, what will happen is the momentum will be increasing. The collision between the particles will be higher. So when particles momentum higher, the force will be higher. Definitely the pressure will be high because the area and the volume related to that. So that's why when volume going down with the same kinetic energy average, okay, then you to have increment in pressure. Same goes, let's say you have the same kinetic energy related to volume, high volume, okay. So it separated very far away. So then the probability of collision will be reduced. Okay. Okay, so why the pressure going down. Okay, so the basic of it, right? So no. Basically, when you have a small area, then you need to have the fluid continuum. Okay, it's going to be continuous in particular system. Okay, so as the pressure difference increase with the amount of air, then you're going to have changes in the pressure. Okay, so why? Okay, when you add tires, right? You normally fill up the amount of air in your tires. What you hit in the pressure gauge is normally actually indicates zero at the local atmospheric temperature. Okay, so what see gauge, okay, towards the gauge, actually the absolute pressure minus the atmospheric pressure. Okay, so to okay, then we're going to have pressure gauge reading. Okay, so the pressure less than the local atmospheric pressure, the surrounding that we have, we call under the vacuum pressure. Okay, what we right now is related to the 1 atmospheric pressure. So the vacuum pressure will be atmospheric pressure minus the absolute pressure. The absolute pressure is indicates the actual pressure for that. Okay. Here it goes. So for the atmospheric pressure at the sea level, you're going to have like 0.01 bar. So then you're going to have below the atmospheric pressure, you're going to have absolute pressure. Okay, but in this area, so you're going to have vacuum pressure. The atmospheric pressure, you're going to have a gauge pressure. So towards the ordinary pressure, the vacuum gauge pressure. Okay, out of this, they actually come up with the instrument called barometer and also manometer. Okay, so we'll be actually when we use this instrument, we actually measure the amount of pressure. Okay, so as you can see, okay, the bottom is instrument measure the atmospheric pressure. Okay, so we're going towards this. Basically, this is under the manometer. Okay, so force acting downwards. Okay, so actually towards the bottom of the cone, so we're going to consider the gravitational force as well. So towards here, we're going to have the initial pressure P naught at the atmospheric pressure, considering towards the area, the fluid column towards the cross-sectional area of here, and we need to consider the density of that fluid. So the density of fluids play an important role. Okay. We will consider the height. This is the final force, okay, value. Okay, so when m is the mass of the fluid, so let me have a look in my notes if I'm anything. Okay, oh no, okay. So the mass of the fluid column A to a cross-sectional area, okay. So the pressure must be equal when at the lower density, such as the pressure P is equal to PA. Okay. Therefore, the pressure at B minus the pressure, the initial pressure, so you're going to have rho GH here, because considering the anode pressure, the A plus the mg, you're going to actually have the mg will actually relate with the density of the fluid, the height, and also the additional force. Okay, at cross sectional area. Okay. So I already discussed about this thermal equilibrium. Sorry about that. Okay. So we're going to have, okay, when we have thermal equilibrium means there's no changes of temperature. There's no temperature gradient. So it will actually stable at certain phase. Okay. So hot tea, okay, that is my favorite. Okay. So it but it to change within time, because since we are considering the zero law of thermodynamics, so it's going to change the amount of energy towards the surrounding until it reaches at the thermal equilibrium. There will be no difference in the pressure. Like that we have the terms towards the heat and work. Okay, where we discuss about the energy cross the boundary of the system. Okay, so we're going to have two forms of energy. Okay, topics which relate to this energy cross towards the boundary. The first is going to be going to have heat, and the second one we're going to have work. Okay, so the heat is form of energy transfer between two systems. Okay, till it becomes equilibrium. Okay, so the heat is considered transition, and let's say the process take place and equilibrium at certain temperature, meaning with the atmospheric temperature. Let's say here is you can see the Coca-Cola can, the Coke can. Okay, for the temperature is 25 here, and 25 at the atmosphere, indicated that there's no difference in temperature. So this we call it as an adiabatic process. Okay, no changes in heat. Okay, then we have like changes in heat, which is the normally we put the notation of Q. That is the heat changes towards that. Okay. To have a possibility of adiabatic process, you're going to have negligible energy transfer through the boundary. So it's going to be a perfect insulation, and the is the thermos. Okay. Okay. So the adiabatic process will not be the same with the isothermal process. There's no heat transfer for adiabatic process, but for the energy content temperature can be changed with the work. So we're going to have the isothermal process. Consider. Okay. So there are three ways of transferring. Okay. We're going to have conduction, convection, and radiation. Okay. Conduction is the transfer of energy and energetic particles towards the substance. So let's say you have a pot and you fish. Okay. So you can feel the heat. So consider as conduction. Where the convection process, you're going to have solid surface or any adjacent field of action. So this is towards the dynamic process. So when the condense, you're going to have two different what you call that depth. So at the hot area, you're going to have less dense. Okay. Then the colder area, you're going to have higher dense. Okay, so basically, thing will keep on moving to hit the equilibrium process. Okay, towards the radiation is not like what we call radioactive radiation, but is part of the electromagnetic radiation, what we call thermal radiation. So the transfer of heat. So that if let's say you have a heat camera, so you can see the development thing here, okay, of the different what you call that coloring. You have that orange color, the blue color, the red color, right? So you will see that in your thermal camera. Okay, so it's the emission of the electromagnetic wave. So, sorry. Now the word heat transfer associated with force. So normally we know as joule or kilojoules. Okay, so you have it in this particular part. Okay, and we're going to have specific words. So yeah, this we're going to discuss on the chapter 2. I'll just run through, guys. Okay, and the convention of the heat transfer to a system. So you're going to have, like, say, if the heat to the system, you have positive values when the calculation. I just introduce all these things so that you have a general understanding to the thermodynamic topics that we're going to discuss later in coming chapters. Okay, so if let's say going out of the system, it's going to be negative. Going by the system is positive, and on the system is negative. Okay, so here are the notations. Okay, the illustrations that. Okay, now have path functions. Okay, don't worry, we're going to discuss more on the second chapters. Okay. Now, to the circle of thermodynamics, we're going, for example, going to have changes in the volume. We know that we discussed just now, it relates with the amount of area and amount of volume in the three-dimensional. So it will going to be represented by delta V, or sometimes you put it as dV. So that's why we're going to have integration. Normally, when you have integration, you are changing the dimension. So you're going to have delta V. The result, we're going to have V2 minus V1, since we have two different parts. Okay, so and then yes, we'll consider towards the amount of volume that change from stage to the final stage, and it can, in the what you call that, in the ideal situation, it can be reversible. Okay, so however, with work during the process is something like the delta W. Work is considered as the total path process, okay, of the thermodynamics. The whole thing is a work from 1 to 2 to 1, so it's considered as work. The means the whole thing means amount of energy that actually helps with stress. So that's why delta W will be like W2 minus W1. So it will not happen like that for work. But for the you're going to have changes of appearance. Okay. And besides that, in coming chapter, we're going to discuss about the specific heat. Okay. The specific is all about the energy storage for different substances. Okay. So and for water, we're going to have differently. Okay. So you're going to have different amount of energy stored in 1 kilo of water to 1 kilo of air. Okay. So we're going to have different specific heat. So that is under the energy storage. So all these different towards the amount of energy relate with the heat specific that we have. Okay. Now, so the specific heat, we're also going to have constant pressure and constant volume. So this will be quite crucial in our next discussion. Okay. It's so the stick heat for the constant pressure will be always greater than the constant volume. So then I will actually discuss deeply on our second chapter. Okay. So don't have to worry about all this equation. Never mind. Okay, now for the statement. Okay, the final part before I start the session. Okay, so let's say you have A and C. Okay, you bring them together. Say B is the hottest, B and then A is the hottest, B is the medium, C is the coldest. So when it's close to, it's going to reach the thermal equilibrium. We have 35, 25, and 35. Okay, so that's what is Zero's law is all about. Okay. So the statement is very simple, but it's a basic fundamental towards, it's really fundamental towards the understanding of thermodynamics. So when it's in contact, in thermal equilibrium, if both have same temperature. Okay. So now A is what surrounding. Surrounding will be 25. Okay. So if D is 25, even not contact with each other, so it is stated as the thermal equilibrium. A and B are in thermal equilibrium. Okay. Okay. So okay. Please have a look on the notes that I already upload. Okay. I also upload some questions how to relate it to the pressure. Okay, those chapters. So we're going to see on the first, I think, 21st October, related to the second chapter, and it's going to be a bit deeper this, okay, the equation. So be prepared with all your derivative knowledge, the integration knowledge. Okay, we're going to use that, but we're going to go step by step. Don't worry about that. Okay, so I think that's it from me. Okay, to meet again. Thank you very much.